Okay, so this is where we ended up, and we're on chapter 3. We're a little bit behind. We actually should be finished with 3 as of yesterday, so we're behind. But I think everybody else that I'm talking to about this 8-week thing, they're going, yeah, I'm behind. So I don't feel so bad. We're behind. I guess we'll figure out what to do about all that. At some point, this is kind of a pilot program. It's what it really amounts to. We're all the guinea pigs. You and all the instructors. We are all guinea pigs. I guarantee you. So maybe we'll get it together. You never know. Maybe we won't. I'll be back. That was fun. All right. Okay, what you're looking at here, these are really what we call the functional groups. Okay, a functional group. These are groups of atoms. Yeah, if you want to chat, if you wouldn't mind just stepping out, that'd be cool for the other people. I don't particularly mind if you want to chat in, have a good time, take your clothes off, run around the room. Really isn't going to disturb me at all, but it might bother somebody else. So, yeah, you want to chat, there are plenty. We've got real comfy chairs right over here, very comfortable. You can lounge out, probably between classes. Y'all could get in a little copulation. Nobody would notice. Get behind the sofas. I don't really have any clue, what you're looking for, but possibly could happen. There's always a parking lot, automobiles. Yeah. You're young, I understand. Bathrooms typically empty this time of day. Yeah, sure, okay, but but anyway, this is class for the moment. All right, so we have what are called functional groups. These are groups of atoms that attach to molecules. So these are highlighted, like, for example, BOH, called a hydroxyl group. You find these a lot on, like, alcohols, the OH group. That's actually ethanol, so this is what you would find in any liquor or any beer. It just depends on the concentration and, of course, how they're going to what barrels are going to store that in, and what grapes they're going to use, or what they're going to use for a fermentative process, whether they're fermenting hops or barley, or whether they're fermenting grapes or whatever. You get different kinds of alcohols obviously out of that. But you also find OH groups in many things. It's called the hydroxyl group, which is labeled right there. And sugar has several little hydroxyl groups. So that's a functional group. It gives it very distinctive characteristics. Obviously, alcohol has several distinctive characteristics that go along with it. Here's a carbonyl group, carbon with a double-bonded oxygen. You see this right here. That's a aldehyde, what you would get in, say, like formaldehyde, which they used to use in pickling or preserving, if you prefer. Your, say, like pigs that we use, they don't use that anymore. It turned out it was a carcinogen, so obviously we don't want to use it. They use a different kind of substance now, which to our knowledge is not a carcinogen. It doesn't really matter when we do that in semester 2. We put on latex gloves and not need to worry about that. And then here's a carboxyl group, very common. You'll see that. It's a carbon, double-bonded oxygen, OH, carboxyl. And then the amino group is an NH2, and you see that quite often. The phosphate group, which is a PO4. And there's several ways you can write that. Notice it has an OPO3 minus 2. It looks really complicated. Usually I just put a PO4 line out there, meaning it's attached to something, some molecule. It's an easy way to do it. Sometimes you'll even see it just written with a P and a line around it. Phosphate group. And then sometimes you'll even just say, like you'll have a molecule, and because it's so common and we use it so often, there's several different abbreviations. They'll use PI. The I stands for inorganic, meaning there's no carbon here. Notice you don't see any carbon in this. This one actually has 3 phosphates. You got a phosphate here, and a phosphate here, and a phosphate here. This is adenosine triphosphate, also called ATP. This is what we use for energy to do anything. So when we eat our foods, other than building blocks, which we use to repair things that cells die off and hopefully get replaced, that works really, really well. From about age, depends on if you're male or female. If you're male, you're physically an adult at 21. So until conception, until 21, you're actually going through a growth period. So it's a building period. And if you're male, then from 21 to 30, cell death and cell production are equal. It's the same. So if a cell dies, you replace it. If a cell dies, you replace it. So you have about 9 years there where that happens. And then at age 30, cell death exceeds cell production, which means more cells are dying in your body than are being replaced. And so death begins at age about 30. That's when it starts. And you're kind of in denial from age 30 to age 40, and usually in denial through your 40s. And when you hit 50, it's like, forget it, I'm dying. Yeah, I can tell. This doesn't work, that doesn't work, this hurts to do that, it's, it's shoulder, this, you got all kinds of problems. You're like, I'm on my way out. Luckily, there's always the doctor, and he has a prescription pad. Yeah, that's very handy. I like that. Once you get up to 50, they're just like, what do you want? They don't care. You want opiates? All right, here, bro. And take some opiates. Yeah, you'll love these. Anyway, it's hard when you're younger, so they're really hard to get. But you get about 50, then whatever. The older you get, they're just like, heroin? Sure, right. You want some heroin? Great. Got it here. Just go up there. Cocaine? Sure, get it. No, they don't write those scripts anymore. Morphine, maybe. You have to be in pretty bad shape for that. But they have other things they can give you. Anyway, but for women, it's a little bit different. You obviously mature at a little bit earlier age. Women typically mature about 15, physically mature at that age. And then from 15 to 30 again, your cell death and cell production is equal. So cell dies, you replace it. And then from 30 to 40, cell death exceeds cell production, so death begins about 30 for all of us. That's just the way that is. All right. Okay. So what we do with the foods that we consume, we use those and we replace cells that are dying off, and that happens less and less as the older we get. But we still do some of that. And then also, if you cut yourself, you're going to replace those cells. So obviously you need some nutrients in order to be able to do that, rebuild those. And then we also need some energy to do that. So some of the food that we consume, we use the energy out of that food to make this stuff right here, because that is what we use as an energy currency. If you want to do anything, you're spending ATPs. So we make these things, we store these, and then if we want to do something, then we spend the ATPs. If you want to run around the track, you're going to spend ATPs. You can only run around the track so many times. Some of you can do that better than others. But at some point, you're going to run out of ATPs, and you're just going to have to sit down. It's called fatigue. You basically run out of oxygen, which is necessary to produce the ATP. You're already out of ATP, and you can't make any more of it, so you are exhausted. and you are fatigued, you sit down and rest and eventually make more ATP, and then you can get up and run around the track a few more times if you want to, do something else. But that is our energy currency right here. We'll talk a lot about ATP. Here's a methyl group. It's a CH3 that may be a little bit hard to read. Methyl group, you'll see a lot of those. That is not by any means a complete list of what we typically refer to as functional groups, but it's not a bad list. Those are very, very common functional groups, and certainly you need to know what those are. You'll see those from time to time, and they do affect the way the molecule behaves. Like, for example, if you have an oxygen, say like in this group, if you're dealing with a carboxylic acid, you've got a carboxyl group right there. Well, you have an oxygen in there, and you notice you even have a second oxygen. And oxygen is electronegative, so it tends to pull the electrons from this part of the molecule this direction. So the electrons tend to pull towards the oxygens, which is going to mean this molecule is polar. This end is positive and this end is negative at that end. Anytime you have oxygen, you know you're going to have some draw for electrons. Well, look at this. You have 4 oxygens here, you have 4 oxygens here, you have 4 oxygens here. So you've got this tremendous pull of electrons headed this direction. So this end of the molecule will be incredibly negative. This end of the molecule will be incredibly positive. So yeah, the functional groups, they definitely have an impact. Here again, you've got oxygen. You know you're pulling electrons this direction. Oxygen, you're pulling electrons this direction. That is going to have an impact, no question. So once you understand a little bit about electronegativity, it helps you to really understand molecules and how they function and how they're going to interact with other molecules, which is fun for some people. For me, I think it's fun to think about those things. Okay, now these are the 4 classes of molecules, and sometimes they're called the macromolecules because they're pretty big, or they can get big. So these are what we typically use to build cells or to build any living organism, whether it's one cell or multicellular, or no matter what it is, a tree, a fungus, an animal, doesn't matter. We're all made out of this right here. Carbohydrates, you're probably familiar with those to some degree. Basically sugars, starch, a few others that we'll talk about. Lipids, those are your fatty compounds, fats, oils, waxes. We'll get into all this. You don't have to write it all down. It will all be in there. We'll talk about each one of these separately, so there's really no need to write. Unless you just kind of like taking notes, it helps you to remember things, which I think is cool. I'm not really sure what I'd do if I were in your shoes, whether I'd take notes or not, because it's all on the PowerPoint now, and it's in the book. Right, well, that's cool. The thing is, on so much of this, I cut out the text, and I just leave a word, and I describe it. So I am going to, though, start giving you the entire PowerPoint presentations. That's what you're getting, and I've cut it down for class to a manageable, hopefully a manageable size, so we can get through it in the time frame that we need to get through, which we're not doing that. It's not working very well. Okay, proteins. This would be things like any meat, which is muscle. Any muscle, whether it's on a rattlesnake meat, never eaten that, but want to. Cow muscle, pig muscle, goat muscle. My granddad used to be able to cook cabrito like no one else. That's hard to make. I've tried to cook cabrito. It's tough. hard. It's tough meat, and it takes someone who knows what they're doing to do it. But I love cabrito when it's done well. Anyway, any kind of muscle. Egg white is protein. Many other things. Anyway, and 55% of your cell membrane, each cell, the membrane around every cell of your body, 55% is protein. So we have a tremendous amount of protein in our bodies. The nucleic acids, one of which you're very familiar with, DNA, carries your genetic information. Half of that you get from your biological mommy, and the other half of it you get from your biological daddy. And that makes you. You're 50% mom, 50% dad. And when you have a child, that child will be 50% you, which I think is very cool. Which will also be a quarter your mother and your father, and a quarter the other person's mother and father, which means 25% the mother, 25% your father, 25% the other person's mother, and 25% the other person's father. A quarter. So, if you die and you have children, you're really never dead. A piece of you always moves forward. It always goes forward. Interesting to think about those kind of concepts in biology. I think those are kind of fun. Of course, I have cats. When I'm dead, I'm just dead. I'm just dead, gone. Yeah. I have some people that are next door neighbors, and when each one of them passed away, and recently, and of course that's typical when the wife dies or the husband dies, and it isn't very long before the other one dies. That's very, very typical, because they're like, well, I don't want to be around if the other one's not here, and they just die. It's just very, very common. Anyway, and they did not want They didn't want a funeral service. They didn't want it even put in the paper. They just wanted to go and just disappear from the planet. And I thought that was very interesting. I've never known people who did that. It's like, nothing at all. I've had children, so they could have had funerals and the whole thing, but they just didn't want it. I never heard of anyone doing that. I didn't know. I always thought you had to. It was just something you did. And I kind of liked it. It's like, well, you just go. Big deal. What? There's gazillions of people. We'll continue to have gazillions of people. We need to all have little funerals and, pallbearers and all that. Kind of strange. Anyway, okay. So let's talk about these macromolecules. It just tells you big, huge molecules. Macro, large. Macromolecules are really polymer. Poly means many. If you bust this word up, poly is many, and mer means unit. So this means many units. So let's just divide that, many. And again, mer means unit. So I have one unit bonded to a second unit, bonded to a third unit, bonded to a fourth unit, bonded to da-da-da-da. At some point it stops. But that's a polymer. A monomer, mono means single, or one. Single, mer means unit. You have a single unit. So any one of these circles would represent a monomer. So monomers make up polymers. Polymers are just long chains of individual single units. And because of that, they're huge molecules, so they're macromolecules. Kind of went in reverse with this. So you have these monomers, single units, that bond together to make a polymer called polymerization. That's what they do to make plastics, rubbers like your tires. Those are just polymers. They have plants that polymerize, hydrocarbon plants that polymerize things and build, tires or plastics or whatever. Big polymers, big huge molecules. But they're made out of repeating units, just thing to thing to thing to thing. You just got to know what those things are. So carbohydrates, You know, if you're dealing with a polymer that's that's a carbohydrate, it's nothing but a sugar bonded to a sugar bonded to a sugar bonded to a sugar bonded to a sugar. Something like starch. Starch would be, say, a potato. If you put a potato in your mouth, it's starch. We all know that. It doesn't taste sweet, but it's just made out of repeating sugar units. It's nothing but sugar bonded to sugar bonded to sugar bonded, and it continues. Starch is potato. Same thing with a cracker. It is nothing but a long chain of sugars, and it doesn't taste sweet. It's a starch. Any flour product is a starch. So you can buy all kinds of starches. You can buy cornstarch. You can buy potato starch. You can buy rice starch. You can make breads from all kinds of different things. Buy flours of different types of there are many different types of flours out there, but basically they're all starch. They're just chains of sugars, but obviously they don't taste sweet. As long as they're bonded together, sugar to sugar to sugar to sugar to sugar, they don't taste sweet, and that would be a starch. Obviously, it is a polymer because it is a monomer sugar bonded to a second monomer sugar bonded to a third monomer sugar, and so forth. So you got a polymer, sugar to sugar to sugar to sugar, and it's a huge molecule. So starch is huge. And that's just to give you an example of how these molecules will be built. That's how we build them. So, you know, if you understand what the monomer is, and then you go, okay, so you just bond one to the next, to the next, to the next to get the big, huge molecule, then you understand the big, huge molecules. So it's really not all that complicated. Some people go, oh my gosh, we're looking at all these big old molecules. This must be very hard. It's, you know, just understand what the monomer is, and all you're doing is repeating it. One bonded to a second, bonded to a third, bonded to a fourth. Okay, and there are different ways that we can bond things together. Basically, one way is predominant, called a dehydration reaction. Means that if we wanted to bond two monomers together, so we had this monomer and we had this monomer, what we do is we pull out the water between the two and we create a bond between the two. This is called a dehydration reaction. That totally makes sense. You pull the water between two molecules, that's a dehydration. To dehydrate. Pull out water, remove water, dehydrate. Totally makes sense. Okay, so that's a dehydration reaction. But what if I had, say, like, for example, I had a long chain of sugars, and we'll just use that carbohydrate as an example, blah, blah, blah. A long chain of sugars, call this a starch, like a potato, a bread, a cracker. What if I wanted to break the bond and pull off a single sugar? What if I wanted to break that up? Well, one way that you can do that is to add water back into it, to put the water in, and it'll break that off. That's called a hydrolysis. Hydro means water, Latin for water. Hydrolysis is Latin for to break. So you break something apart using water. It's a hydrolysis. 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 So a reaction where you break something apart putting in water, and we do this a lot, that's what you do with the foods that you eat. If you eat meat, which you may be vegan, I don't know, or vegetarian, and not eat meat, I've been on that kind of an eating regimen before, where I didn't eat any meat. I did that for a long time. But, you know, we're kind of we crave meat. We really do. So it's really hard to stay on that. But I like to eat like that. And therefore we do not kill the animals, which I really like that a lot. Biologists are a little different, but you know, it's a big world. But yeah, no, bless you. Bless you again. Bless you for the third time. Yes, triple sneezer. I understand. Absolutely. I'm a triple sneezer. Absolutely. Anyway, so yeah, you break something apart using water, hydrolysis. So we eat, a lot of us eat meats, you know. Well, we have to break that down into the individual units that make up that protein. Protein is the same thing. You know, it's not obviously sugar to sugar to sugar to sugar, but it's something to something to something to something. Protein like meat, you know, it's something to something to something to something. It's monomer to monomer to monomer to monomer. Well, we have to break that down because each one of these has to be released, and then we have to absorb that into the intestinal tract. I'm sorry, we have to, this is in the intestinal tract, excuse me. This breakdown occurs in the intestinal tract. So let's make a long intestine. So you swallow food, eventually it goes into the stomach and it's broken down a little, and then eventually it goes to the duodenum, which is the very first part of the small intestine, the duodenum. And that's where you do most of your digestion. People think digestion occurs primarily in the stomach. Wrong. Stomach is primarily a holding chamber. It just holds the food. Keeps it, hangs on to it, and then a little bit of it is released into the duodenum. The duodenum's about the first 10 inches of the small intestine. And a little bit of food goes into that duodenum, and it's all broken down by enzymes produced by the pancreas. That's where those enzymes are produced. If you didn't know what the pancreas did, it does produce the majority of digestive enzymes. But, you know, this is where the hydrolysis occurs primarily. So you break off these individual units, and then once you break them off, then they can be absorbed by the body. But you can't absorb something that's just a polymer, a long chain of units. It's too big to absorb. You just have to break it completely down into individual monomeric units, single units, and then you can absorb them. So something like a cracker, you eat it, you chew it, you swallow it. Most of it will just hang out in the stomach for a while, and then a little bit of it will squeeze in the duodenum, and then you have enzymes secreted by the pancreas that will break that starch, nothing but sugar to sugar to sugar to sugar, into individual sugar units, and then they're absorbed. Get into your blood, move around, go into the liver. We can do different stuff with it there, but it's kind of fun to understand how all that works. For me, I like that. It certainly helps you to understand nutrition. Enzymes are protein catalysts. That's what they do. They catalyze reactions, which means they speed up reactions. Protein catalysts. And so they speed up reactions. We'll spend a tremendous amount of time talking about enzymes. Most reactions that occur in a living cell, which would be you've got 70 trillion of them, occur by enzymes. So yeah, we'll spend a lot of time talking about enzymes. I don't feel the need to even broach the subject at this point, other than to just say that, you know, whether it's a dehydration reaction or hydrolysis reaction, dehydration means you're pulling out the water to bond things together. Pull out the water to bond things together. Hydrolysis means you're adding the water in to break things apart. Whichever way you're going with it, typically you need an enzyme to make those things happen. Things just don't spontaneously fall apart in the body. Not molecules, big polymers, and things don't automatically just bond together. If you want to build more muscle, you've got to have enzymes to put the things together to build more muscle. It just doesn't spontaneously happen. It's like, oh, I need to bond with that thing. Yeah, I'll jump over there and bond with that thing. Something has to make it happen, and that would be enzymes. So very critical, major part of those reaction processes. All right, and we'll go over that till you're probably sick of it. I don't think our animations are playing yet. I've got to check with the textbook person to figure out why my emanations why my emanations aren't working. And she go, what are you drunk? Not at the moment. Check back with me later. I may be. No. Friday night's usually my night to drink. Not Saturday. I need 2 full days after a good amount of alcohol. Totally detox. Just get it out. You know. But 1 night a week to just twist completely. You know. And your liver can handle that much. But if you go over that, your liver's going, not good, not good. You can twist 1 night a week. You go over that, you're going to end up with some problems. And I know these things. So I'm just like, okay, it's my night. Yay, oh yeah. You know, but, you know, usually there are only 2 of us. So I don't make a fool of myself in front of a lot of people. Which, believe me, I would love doing that, but I know better. All right. You know, it's kind of fun to watch a 20-year-old make a fool of themselves. But, you know, when you get to be 58, it's not pretty. You don't want people watching that. Okay. Although it is a lot of fun, for sure. Okay, proteins. So let's talk about those. What is the individual unit that makes up the protein? The monomer, the individual monomer. Well, it's called it's an amino acid. That's what it is. And there are 20 different amino acids. So, you know, you could bond amino acid 12 to amino acid 3 to amino acid 20 to amino acid 14 to amino acid whatever, a particular sequence. And you would make brown eye pigment. You would have brown eyes. And if you bonded amino acid 19 to amino acid 4 to amino acid whatever, and a different combination, you would have green eyes. So depending on which amino acid you bond and in what sequence they are, you have a different protein. You can make a muscle protein, you can make a eye pigment protein, you can make an enzyme protein, you can make a cell membrane protein. They're all built out of individual monomers called amino acids. DNA is also built out of monomers. They're called nucleotides. So they are also nothing but a nucleotide bonded to a second, bonded to a third, bonded to a fourth, bonded to a fifth, a long chain of nucleotides. So, you know, you bond all those together and you have DNA. It's not all that difficult once you see all that happening. So here it is, just kind of, and I did this sort of on the board. So if I wanted to dehydrate, so I'm pulling out water between this monomer, which is this purple sphere, and this purple sphere over here. I'm going to bond this purple sphere to these over here. Okay, and all I have to do is pull out water. That means to dehydrate, to pull out water. It's a dehydration. And once I've done that, I've created a bond. So pulling out the water creates this bond right there. So it's a dehydration reaction, sometimes referred to as a condensation that happens, to condense. You know, water comes out of the air and condenses around a glass if it's cold on the exterior, particularly if there's humidity in the air, and there is quite a bit lately. It's supposed to rain Friday, Saturday, and Sunday. Farmer's Almanac says it's going to be a rainy fall, and it's usually right. I don't know who in the heck writes that thing, but it's kind of spooky to me. Like, who writes that? Where did they get their info? You know, Farmer's Almanac. You know, it sounds like farmersonly.com. You know, you know. Oh, if you're a farmer and you want to hook up with another farmer, go to farmersonly.com, you know. Like, oh my God. I will not be going to Farmers Only. think so. Craigslist in a pinch. Oh, God. I know. That's an audible. Oh, God. Yeah, I agree. All right. Okay, so we're bonding things together by pulling out water. That's a dehydration. Now, if I want to break something apart, if I want to break that last monomer, little purple sphere off, I add the water in. That's a hydrolysis, to break using water. Dehydration means to pull out water. Well, that forms a new bond. It's where we get a new bond. A hydrolysis means to break using water. So I'm going to break this bond right there by adding in water. And I break it apart. So again, here you're doing either you're putting things together by dehydration or you're breaking them apart by hydrolysis. And those are very common reactions that happen in all cells of your body, commonly going on all the time. While you're awake, while you're asleep. Always happening. Okay, now carbohydrates. Carbohydrates are things like all of your sugars, again, all of your starches and some other things that we'll talk about. But basically, carbohydrates have a carbon to hydrogen to oxygen ratio. So a carbon to hydrogen to oxygen ratio, and an approximate 1 to 2 to 1 ratio. For example, we can use, say, a glucose, very common sugar. You'll get tired of hearing about that one. C6H12O6. So that is a sugar that we use to produce ATP, our energy currency. So it's a 1 to 2 to 1 on carbon, hydrogen, oxygen. But if you wanted to, for example, do a sucrose, now the sucrose, which is table sugar, that's everyday table sugar. White, granular, table sugar. You buy it in the grocery store. You want to bake a cake, use table sugar to do it. I buy my sugar from Mexico. The Mexican sugar is actually made from sugar cane. American sugar comes from sugar beets. And sugar beets have a little bit of a bitter taste. And the cane sugar that you get, that the sugar in Mexico is made from, has no bitter taste to it. So if I start to run low on sugar, typically I'll ask my classes, is anyone going to Mexico in the next month or so to visit family, whatever? And I can find someone. Yeah, I'm going over there, and whenever, I won't be there till December. I'm like, okay, would you pick up me, 5 pounds of sugar, bring it back across the border, white powder, it's stuff, just get it across the border. That'd be nice. And bring it to me. I'll be glad to pay for it. It'll be very nice, sweet of you. Yeah. So anyway, so I can pick up my sugar that way. Okay. So sucrose is actually, it's not exactly a 1 to 2 to 1. It's C12H22O11. Now what it's missing, so it's not exactly 1 to 2 to 1. It's pretty close. But it would be exactly 1 to 2 to 1 if I added water in there. So this is actually two sugars that are bonded. This is what you call a disaccharide. Is a one sugar bonded to a second sugar. So that means that they pulled out the water. They did a dehydration, pulled out the water to bond two sugars together. It's a disaccharide, two sugars, sucrose. Pardon? No, it's made, plants make it. Yeah, it's not artificially made. There may be a way to make it artificially. I wouldn't be in the least bit surprised. But like I said, if you're getting it from sugar cane, sucrose, it's the cane makes it. and if you're getting it from sugar beet, there's some other compound in here that I don't like to taste. And I like to make cakes for people's birthdays, nephews, nieces, people I know, whatever. Monosaccharide tells you exactly what that is. Mono means one. Saccharide means sugar. It's a monomer. It's a single unit. It's one of those. So if I want to bond one sugar to a second sugar to a third to a fourth, then I have myself a long chain of sugars, say like starch. But it is the single unit. Now there are several monosaccharides. Actually, there are three. There's a glucose, is a it's a 6-carbon sugar, and fructose. You may have heard of fructose. Some people call it fructose. I'm always afraid I'll slip up on that, so I don't say that. There's galactose. All three of these have the same chemical formula. They're C6H12O6. So same chemical formula, but different structures. So these three are what are called isomers. Whoops, not correct. Iso means same. Mer means unit. Means they have the same number of atoms, 6 carbons, 12 hydrogens, 6 oxygens. They just don't look the same. They put them together in a glucose doesn't look like fructose, which doesn't look like galactose. They're certainly going to look different. But chemical formula is the same. Your body pretty much treats them the same way. But, you know, if we eat something that has fructose in it, you can buy fructose at the grocery store. I wouldn't waste money on it because your body will convert it just immediately into glucose. The liver does that because we run primarily on glucose. Even if you're going on a carbohydrate-free diet, you don't eat any kind of food that has any sugar in it or starch in it, and you're totally carbohydrate-free. No breads, no flour products at all, no crackers, no potatoes, no rice, you know, no starches at all, no sugars, period. Your liver can take other things like protein that we consume, meat things, and make it into glucose. Liver's pretty clever. Liver's the interior organ. Your organ is? Yeah. Your boyfriend penis. That is not correct. Tell him no in biology. They actually told me it was the skin. Yeah. So forget that. Put that away. Anyway, so same unit on these, but different structures. So the liver can actually convert all these into glucose, which it will do, make those into glucose. And then, like I said, if you're carbohydrate-free, which some people do that, then that's also going to be converted into glucose molecule. Some of it anyway, because we have to have that glucose in order to survive. That is what we run on, for sure. Okay. So here's glucose and fructose. All I want you to see here, obviously you don't have to know these structures, but I do want you to be able to look at that and say, well, if I wanted to count the carbons and the hydrogens and the oxygens, it would be the same for both molecules. They don't look the same. They're both C6H12O6, but they are put together a little differently. So they're isomers. Iso is same, mer is unit. You know, all those biology terms that people tend to dislike because they sound really strange, they're Latin, and Latin is very descriptive. If you know what the prefix means, you know what the suffix means, you already know what it is. Iso is same, mer is unit. I mean, you have to extend that a little bit. Same number of atoms, different structures is really what that refers to. But I like Latin, actually. Different ways you can draw this. Now, this is a glucose molecule, right here. And, you know, you can draw it with every carbon. So carbon always has 4 bonds. So this is the first carbon, carbon 1. And they number the carbons beginning at the right, going around. So first carbon is right here. Carbon has 4 bonds. If you count the number of bonds to that first carbon right here, then you'll see that it actually has 4. It always will. It has to be stable. So it has 4. Hydrogen will always just have 1 bond. That one just has 1. This oxygen to hydrogen, it actually has 2. The way that would be written really would be the carbon would bond to the oxygen, which would bond to the hydrogen. So really, that oxygen right here, they're not showing the bond between the oxygen and the hydrogen, but there is a bond, covalent bond. They just don't typically put it in there. It's so common, that hydroxyl group is so common, they just don't throw it in there. Put a little line showing you that. So it's already an abbreviated structure just by not putting in a bond between the oxygens and the hydrogens. It's already abbreviated. But other than that, they pretty much put in every bond that you have. Now this number 6 carbon, you have CH2OH. They didn't draw that out, but you'd have a carbon with 2 hydrogens. This is attaching to the stuff below. And then you have that to an oxygen, which is bonded to a hydrogen. So that's already abbreviated, this thing right here. Oh, I didn't put my hydrogens in. So yeah, it's abbreviated. But you can abbreviate it even more. You can, wherever you have a carbon, you just have a juncture of 4 lines. 1, 2, 3, 4. So that little point right here, there must be a carbon there, must be a carbon here, 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 here. All right. So anytime you have a juncture of 4 lines, that would be a carbon. So that's abbreviated structure. I don't do this simplified structure. That's way too simplified. Students go, huh? What are you doing? But yeah, we can pull the carbons out. It's got a juncture of 4 lines. It's carbon, obviously. So I don't tend to do that one. Or I do that abbreviated structure quite a bit. We'll be seeing those. From time to time, we'll be working with that one. Okay, now a disaccharide. Di means 2. Saccharide means sugars. So it pretty much tells you what you're dealing with. You're dealing with 2 sugars. Di is 2 sugars. And I've already talked about that. An example of that would be sucrose, table sugar. Sucrose is a glucose bonded to a fructose. So this sugar is glucose, and that sugar right there is fructose, F-R-U-C, fructose. So there's one disaccharide. A second disaccharide would be lactose, milk sugar, what you find in milk, no matter what mammal it comes from. All female mammals produce milk to nourish the young. We understand that. But again, you do have 2 sugars that are bonded together. One of those will be glucose again. We see glucose so much I begin to abbreviate it. The other one will be galactose. So that's a disaccharide. And the third one is what we call maltose. Maltose is malt sugar. If you've ever had a malt instead of just a milkshake, they add a sugar to it, just a spoonful of sugar in there. Really, it's a pretty big chunk amount. But anyway, it makes it even sweeter. Malts are pretty tasty. And that's a glucose bonded to a second glucose. So those are 3 disaccharides that we find on carbohydrates. It's where you have 2 sugars bonded. Obviously, if we wanted to break them apart, we would put water in to break that down. That would be a hydrolysis. water goes in to break it apart. Hydrolysis. Okay, so those are disaccharides. And then we look at our, oh, that won't work. There we go. There we're going to pull out the water to bond the two together. So if we pull out water, not put in water to break it, but we're pulling out the water, that's a dehydration. We're pulling out water. So that's a dehydration reaction right there. Okay. Now polysaccharides are long chains of sugar. Nothing but sugar, bonded to sugar, bonded to sugar, bonded to sugar. We've already talked about that. Starch is a very good example of that. And this just goes on and on and on and on. So examples, starch. That's what plants store. They make sugar. They do this real process, very clever, called photosynthesis, and they have the ability to make their own sugar, their own food. We can't do that. But if they make an excess of sugar, they store it as starch. We do store excess sugar, but this is plant storage, carbohydrate storage. We do the same thing in our livers, although we call it glycogen. So animal. Sometimes they just refer to it as animal starch. You store it. We all store glycogen. If you want to lose the fat off the body, you have to get rid of all of the glycogen that you stored in the liver, which means you have to go pretty hungry because your liver's packed full of glycogen. So you have to go without food for a long period, and then you pull all the glycogen out of your liver and release it, and you run off all that sugar because it's just sugar to sugar to sugar. You got to break it all down, release it as individual sugars, and then you have to burn all those sugars. You have to use them. And once all those are gone, then you can begin to get at the fat. But you got to get rid of that first, and that's why diets are not a whole lot of fun. People don't like them. They're tough. And I've been on many diets. I do diets quite often, actually, which is crazy. But anyway, I do. Anyway, starch, glycogen, cellulose. Cellulose, this forms cell walls for plants. We also have another name for it. We call it fiber. Fiber. It is not digestible. You cannot digest it. So plant material that you eat, salads, green beans, peas, doesn't matter. The cell walls of each cell has cellulose around it, and therefore we can't digest it. So it goes in one end and pops out the other end. We can't digest it. And when it does that, it moves through the intestinal tract, and it tends to scrape out fat that lines the intestinal tract because we tend to consume more fat than we're supposed to. And what happens is you begin to store a lot of dyes and preservatives and all kinds of things that we really don't want stored. We want those to pass through the body, and they're not going to be absorbed into the body, and therefore we want them to pass out. But if we have fat lining the intestinal tract, they will accumulate in that fat lining, and they can create an irritation to the intestinal lining, and that creates colon cancer, which you're not going to want. Colon cancer can kill you for one. If it doesn't, at least take out a pretty good chunk of your colon, and then you'll have your colon, which then they actually attach your colon to the side of your body. And then they attach a colostomy bag to that. So every time you want to poo, you poo into that bag that is attached to your body. So you could be like having dinner with friends and pooing at the same time, or walking, going to class and pooing at the same time. You have to go empty your colostomy bag. You probably wouldn't enjoy that process very much. Like, excuse me, it's full. My bag's full. I got to go pull it off. Not a pleasant thing. So that's why they say you need to eat a lot of fiber. That begins now. I mean, you can't start eating fiber, too much of it, too soon. You know, that fat starts collecting on your intestinal tract really early. And so let's clean it out. Eat lots of fiber. It's a very good thing. Or take Metamucil, or there are all kinds of things you can consume that will clean out that fatty layer, and you'll prevent your colon cancer. Because when you get to be my age, you know, I mean, when you turn 50, one of the first things you're supposed to do is go in for a colonoscopy. Thank you. And they actually they knock you out, and then they put a camera up your rear end to take a picture of your inside. Just move it all the way through your intestines and take photos. Like, oh, we're gonna view his, you know. Anyway, that's welcome to the wonderful world of getting older. But yeah, clean it out now. Get it clean. Clean out that intestine. Have a good day.